So let's just start, and I think like people will join us. Hello, everyone. Thank you for joining us for another machine learning launch seminar at Vanderbilt University. Today, we are delighted to have Nick Cheney here. And Nick is an assistant professor of computer science at the University of Vermont. He directs the UVM Neurobotics Lab and is a core member of the Complex Systems and Data Science program. Nick received his PhD in computational biology from Cornell, and he did a postdoc in University of Wyoming working with Jeff Clune. He has served as a visiting researcher at the Santa Fe Institute, NASA Ames, and Columbia University. And Nick's research aims to lower the barrier to machine learning by producing more robust, scalable, and self-configurable neural network algorithms and architectures. He specifically focuses on meta learning, and we are very excited to have him here today. Nick, the stage is yours.
Great, thanks so much. Thanks for the invite to talk, and thanks for all of you for sharing your lunchtime with me. I will have a fairly ambitious talk here. Rather than highlighting a paper, I want to try and get across a perspective about how I think some ideas from embodied intelligence in evolutionary robotics and bio-inspired robotics more generally might play into the design of deep neural networks. I am definitely missing out on all of the discussion we would have on this kind of afterwards in a typical seminar visit. So my email's here. Please feel free to reach out with any thoughts and ideas, and I'd love to kind of carry this on further than we have time for here today. So, as you mentioned, I direct the Neurobotics Lab at UVM, which is doing research in machine learning at the interface of neural networks and robotics. And my background is similarly doing research at the interface of AI and robotics from a mechanical engineering lab, actually. So there I kind of learned and honed my chops at robotics research, and have kind of, since becoming a faculty member, tried to apply that to deep learning more broadly. So in particular, I did a lot of work in bio-inspired robotics and especially evolutionary robotics. Now, this argument I want to put forth today about applying these to neural network architectures, this idea of taking inspiration from evolutionary computation and evolving neural network architectures is certainly not mine and certainly not new. And some of the kind of earliest work in neural architecture search is attributed to folks like Ken Stanley and Risto Mikulainen with the need and hyperneed algorithms, and Jeff Clune with a lot of his contributions to this field too. So the point that I want to make today, I think, is a little bit more nuanced than simply we should be evolving neural networks, but is about a particular way in which robots behave and how they're optimized, which is that robots are these real physical systems that are situated and embodied in the world around them, and they exploit the rules and the physical environment to create complex and adaptive behaviors. And I want to put forth an argument that we can think about that same framing, replacing physics with data and replacing robot bodies and brains with neural architectures and their weights. So the idea of these brain-body environment systems has been around for a while, and I attribute a lot of these graphics here to Randy Beer, who ran an IGERT program at Indiana University on the topic. And he talks especially about these interfaces between the brain and the body and the environment as places where kind of interesting interactions happen. The field of soft robotics especially has been one in the robotics literature where these interactions of brain, body, environment systems are especially important and talked about today, kind of given how much complexity there is between a soft robot and the physical environment around it. And this is where I'll draw a lot of my inspiration from the robotics examples that I'll talk about today. But I'm actually not so much a roboticist myself. I'm more interested in intelligence and AI. And so the part of this which I find most fascinating is morphological computation. The idea that these physical properties of the body can perform functions that are normally thought of as intelligent or attributed to the brain. And thinking about how we can take that same idea and find behaviors and performance within a deep learning system that we can attribute to the architecture instead of the weights, I think is an interesting framing for the types of problems that we're facing right now. I'll start with an example. So on the left here, we have the shadow robotics hand that's extremely well articulated, has 24 mechanical and control degrees of freedom, runs these really complex closed loop controllers. On the right side is a robot from our lab in grad school that has infinite mechanical degrees of freedom, so to say. It's a soft robot that can take on any shape and just one control degree of freedom and runs a simple open loop controller. Oops. The shadow hand is articulated in these really interesting and complex ways with very intentional dexterous manipulation. Where on the other hand, the granular jamming gripper, so we call it, is extremely simple. The 1 degree of freedom is a vacuum that it's hooked up to. This is a balloon filled with coffee grounds. And when the vacuum's off, this is loose and you can push the balloon around this clothespin and the normal forces of physics will adapt exactly around it. And when you hit the on switch on the vacuum, those coffee grounds jam against each other and hold exactly the form around this shape. So similarly, it's able to grasp exactly around the object, but does so in a way that's determined by the physical embodiment it has rather than some complex controller. The idea that a robot is physically embodied on its own is not enough to necessarily endow it with a lot of morphological computation. We've seen lots of examples, and maybe it's even worse when I show the blooper reel here from the DARPA Grand Robotics Challenge, that robots that live in the physical world, when they don't have bodies that are designed for interaction and robustness, catastrophically fail when the environment or their controllers change or have issues. And this is certainly a caricature and hand-picked examples, but part of the larger argument that I want to make today, which is that kind of endowing the systems that we think about here with effective and robust behaviors in robotics, where we have these brain-body environment systems, and especially where we have coupled co-adaptation between the brain and the body, is something that I want to draw an analogy to our deep neural network systems, kind of both from the pieces of weights architecture and data that are interacting with each other, but especially from the setup of fitting the weights and finding an architecture of being this co-adaptation process, where we get very fragile co-optimization and co-adaptation, like we see within neural architecture search and even things like transfer learning. So the format for today's talk, I want to just name some elements of an embodied intelligence perspective that I think might be helpful and relevant for neural architecture search, and talk about some of the ideas that I've explored in robotics, how I am or might explore those within deep learning as well. So the first is what we've already talked about, the idea of morphological computation, that kind of the body by itself can perform effective complex functions. Whether or not you call these intelligent depends on your particular philosophy, so I put that in air quotes here. But the architecture of a neural network alone is a powerful tool, and in the last couple of years, there's been increased research about these kind of morphologically compliant morphological computation within neural networks. And we'll talk a little bit more about that. The second point is that learning in the body and the brain is difficult. It's a coupled system that has fragile co-adaptation. And some of the lessons from trying to co-optimize these systems, I feel like are ones that we'll have to learn in neural architecture search. And I just want to put forth a couple of examples of how it seems that we're falling into some of the same traps trying to co-optimize neural networks and their weights right now. And then we're still far from really solving the open-ended, continually scalable, bio-inspired robotic design problem. But there have been a lot of tricks and tips that have worked, and in particular, looking at adaptation across multiple timescales is one that's been successful. And I want to talk about how those sort of ideas, Evo-Devo sort of algorithms, relate to meta-learning approaches in machine learning, and how I think we could apply them to neural architecture research. So let's start at the very beginning here. The body alone can perform complex functions. So like the robot we saw before that didn't perform much of its function through complex embodiment, had to think really hard about each step it took, which is very different from the way that animals and humans and even cleverly designed robots are able to navigate the world. Maybe the most extreme example of this is a passive walking robot, one where there's no motors, there's no control system. It's just the particular setup of the distribution of mass, the joint angles, and the limb lengths that let it passively walk down this declined plane. While this is a great example of morphological computation, because it's a performance without any sort of brain whatsoever, this took place in the room next to where my lab was at Cornell. And though it was before my time, I've heard about how much painstaking effort this postdoc took to actually get this passive walker calibrated correctly. And being a lazy computer scientist, rather than do that work myself, I'd rather design algorithms to try and automate it for me. So here, coming from my background in evolutionary robotics, we're going to use an evolutionary algorithm to try and build these systems. Very broadly and hand-wavily, this is some representation that we use to build a robot. Perhaps its brain and its body. We set it to some task, like asking it to run as fast as it can. The ones that don't do so well get sent to the robot graveyard. The ones that do great get their own Tinder profile. And we complete the virtuous cycle with a new generation of offspring that kind of iterates until infinity or until our supercomputer runs out of time. So taking inspiration from the passive walker and thinking about what version of this we could endow with a lot of morphological computation and very little brains, we decided to use soft materials and hook up these 4 types of simulated Jello cubes, where the only control is that 2 of them happen to be oscillating counterphase. And we ask evolution to try and configure these cubes in a way that the resulting robots will move as fast as possible. Another downside of doing Zoom talks is that I'm sure the video quality is not nearly as good as it is for you here on my machine. But what I see are robots that really gracefully and I think kind of anthropomorphically run across the screen in these really graceful ways. Not only that, there's an immense diversity of the type of ways that they approach this behavior. And it's funny that kind of what's under the hood for these is very much the same sort of algorithm as the early approaches to neat and hyperneat for neural architecture search. And understanding kind of the mechanisms behind that and applying it, I think is another great analogy between these 2 systems. Another great part of robotics research is that we can actually interrogate and look at these behaviors as they develop over time. And it's amazing to me that just this evolutionary algorithm with the simple rule that faster things survive can find all of these complex rules and patterns that, you should have front and back limbs. You should use opposing materials close to each other to create articulated muscles. You should have left-right symmetry. All of these things that lead to really complex and lifelike behavior. And the fun part about this for me as a machine learning scientist is that all of this is automated. There's no designer in the loop performing any of this or guiding kind of the resulting behaviors through any intuition. And no engineer would tell you to design a walking robot with no legs but arms that flail around. And yet these things are extremely effective in how they move. And I hope that the same sort of unintuitive behaviors are found within neural network topologies too. So Hillary, do you have a question?
Yes, thank you. Sorry to interrupt. So here there is no policy, no nothing. Like these blocks are essentially doing all of them are doing the same thing at the same time scale, right? Like and by composing them into this structure, you will enable this fast blocking. Is that true?
Yes, exactly. There's no control policy about when a block should expand or contract besides just those two that are hooked up to a central pattern generator oscillating out of phase.
Fascinating. Thank you.
Yeah. Yeah, I find that fascinating as well, and we'll try and put in complex controllers in a few slides here. But first, kind of given this system that can evolve all these funny looking robots, we had to play with it and spent a long time looking at different instances and different experiments we could run. This is one of my favorites. It's a version of transfer learning where we try and play God and look at the development of early life, where things that swim in the water we transfer over to land, and find things that, like, tentacles become early limbs, and that going from land to water, we find completely different types of behaviors and forms. I think that the most interesting output of this is not my own work, but from some of my collaborators, Josh Bongard and Mike Levin, and Josh's student Sam Kriegman, who I think came and talked about this work here at Vanderbilt. Amazingly kind of took this system and evolved lots of soft robot morphologies, and Doug Blackiston, Mike's postdoc, actually built these out of real living frog cells, which totally and completely blows my mind, but is a really cool use of this system. Let me introduce kind of one more framework that we'll come back to throughout the talk, which is not just kind of this fast actuation, but the same sort of kind of very dumb open loop control, but at a much slower time scale, where these red voxels are expanding, the blue ones are shrinking, and the evolution is trying to coordinate their growth in a way that reaches out towards this light source, kind of like a plant slowly developing and growing over time. Now, when we do something mean like ask it has to grow in two directions at once, we find that these soft materials are able to exploit their interactions with gravity and do things like fall out to the sides and grow out as much as they can in both directions, which kind of seems like a trivial behavior until you see the version of this with stiff voxels, where they're not able to rely on that interaction with physics. And instead, they have to use this trick of opposing muscle groups to create curvature and manually point the two limbs out to the side where those two same light sources are. I show you this not because this is the most interesting behavior you've ever seen, but because I think it encapsulates well this idea of morphological computation. And here we have maybe the simplest and most naive, but one of the earliest examples of actually putting a concrete number on how much computation is happening in the body by counting the number of stiff or of expanding versus contracting voxels in these two different settings. And I hope that we can think about some metrics to similarly think about for a given neural network architecture, kind of how much computation is enabled or embodied by different structures that we might consider training on. Okay, so that was part one. Part two, part 1B, I guess, is that neural network topologies by themselves in this same kind of naive, uncontrolled way may also be really powerful. So thinking about the analogy of what the kind of least controlled version of a neural network is, I think that the best analogy I could find is a totally untrained neural network, one where you just randomly initialize it and don't do any learning whatsoever. And it turns out that this sort of network is already used fairly commonly. It's a reservoir computer. You may also know it by the names of an echo state network or a liquid state machine. where here we take some input, we pass it through some big deep neural network, or oftentimes a recurrent neural network for time series data. And then that creates a whole bunch of really diverse features that are randomly generated through this untrained network. And we only train the very last layer that takes these features and tries to do some sort of classification or time series prediction problem. I especially like this not only because it's such a naive controller, but because you can actually swap in kind of any black box system into the part that takes an input signal and creates some complex basis function or a basis set of outputs to feed into a simple classifier, like a spring mass system that feels very much like a soft robot body, or an actual physical soft robot where the input is moving this arm around and the output is kind of how the tentacle here traverses in this tank of water. We've played around with these sort of systems just a tiny bit, and as you might expect, kind of randomly generating a reservoir network works actually surprisingly well, but not quite as well as some clever initialization of a reservoir that still has no training on it, but has some nice features we might want to see in the types of output features from our hidden representation layers in a neural network. I'm being intentionally vague here because this work is still early on and unpublished, but I think this is an interesting area to go down. Another version of this that I find totally fascinating has to do more with network pruning and the lottery ticket hypothesis or supermasks. And here, this fantastic work from the University of Washington, they showed that with a randomly initialized network where you don't train the weights at all, you can prune down to a subset of edges in that network. And that within and the performance of those subsets of the network, if you were to train a network from scratch, doing full SGD on all of the weights with the same size as the pruned network, they would perform worse, which is totally crazy to me and completely blows my mind, but also kind of makes a lot of sense relative to the lottery ticket hypothesis. And I think kind of the potential here of untrained networks, or at least untrained subsets of networks, is really exciting to me. Our work in network pruning is still really early, so I'm not going to share any of our current results here, but we'll just show a kind of fun paper from 5 years ago, where instead of intelligently looking at subsets of networks, we randomly pruned AlexNet here, and found that surprisingly the fall off in performance on ImageNet was really graceful, even with kind of the most unintelligent type of pruning you could imagine. Okay, so step number one, morphological computation. There's something happening within the structure of deep neural networks that can have some surprisingly good performance on things like classification tasks. Step number two, or I guess point number two here, is that the brain and the body are this coupled system that have fragile co-adaptation, and that learning them is maybe not so straightforward as we might have hoped. I came into this learning this point quite naively after finding how crazy cool the performance of our robots before that aim to have simple controllers like that passive walking robot. After doing that, I thought, okay, well, we'll put neural network controllers or more sophisticated central pattern generators inside of them, and we'll have crazy cool robots coming out of this. So coded it up, set up the experiment, put it on the cluster, checked the next morning, and everything's working all right. But come back a week later, and nothing's changed since that first check, and I was really dismayed and spent a lot of time kind of banging my head trying to figure out what was happening here, or searching for bugs in the code. but luckily had the support of a really great community around me and friends and colleagues who listened to me complain about this problem. And it turns out that actually a lot of people had found the same sort of thing, that kind of when trying to co-optimize the structure and the control of a robot, that the forms would find some local optima and converge very early on in training. Which in retrospect made a lot of sense, but kind of wasn't a prevailing idea in the field, because we don't publish negative results like this. So I immediately went and published a negative results paper talking about how hard of a problem this was, and in doing so, tried to visualize the space of robot morphologies over time. So each of these different colored lines is a different robot body plan. And as you can see here, we have great optimization at the very beginning, but very early on in this run, we find that we converge to some local optima and only kind of change our body plan once or twice the whole rest of the experiment. And it's certainly not for lack of trying. You see all these little dots here, the rainbow sprinkles at the bottom of the plot are all new different colored morphologies that we're trying out and hoping will be improvements on what we've seen so far, but all of them do worse and get sent to the robot graveyard. So you may have already guessed it, kind of given the setup to the problem, but the issue here is that kind of obviously in retrospect, this is a co-optimization problem, and there's fragile codependence of the brain and the body in performing the behaviors that we see here. So in particular, this is a bi-level optimization problem. And people are thinking a little bit about bi-level optimization currently in neural architecture search, but I think maybe not exactly in the way that I'm going to lay out here, which is that the behavior of any particular body plan depends on the controller or the brain that's employing that body. So here's a cartoon example of that, of this problem of kind of flatlining fitness, and we have some new morphology that's proposed. Maybe some short-legged robot grows longer legs, and it's in this kind of teenage growth spurt, becomes very awkward and trips over itself and flails on the ground and does all the sort of things that we would typically associate with a not very good running robot. But it turns out that it's not that the idea of longer legs was a bad one. It's just that we've broken the fragile co-adaptation of the brain and body of this machine. And so rather than just optimizing for kind of higher things on this plot that are better fitness, we're going to do a multi-objective optimization, trying to optimize towards the top left corner here, things that are highly fit with very little time of fine-tuning that controller on its new morphology. And so with that, we're letting each new body plan adapt a new controller that's good for it. And kind of unsurprisingly, the longer legs, are able to coordinate and run and jump higher and faster. And this happens again and again with new innovations that build on prior ones. Now, the story I told you is completely made up, but the data here is actually a snapshot of the same exact initial conditions I showed you before, where we got stagnation in those rainbow sprinkles, but now it's a rainbow waterfall of continuous innovation as these new colored morphologies come about and overtake each other again and again for as long as we leave this on the cluster. I find this plot really interesting, but maybe the one that's even more telling for me is kind of looking at the robot behavior or the robot morphologies that come out of this. And like we saw before in the setup, we have robots who start with a diverse set of body plans and kind of very quickly converge into some local optima over evolutionary time on the x-axis here. But when we do this co-optimization of performance and reducing the amount of fine-tuning per new body plan, we are able to escape these local optima and find more global solutions. They're not especially complex here because we've set this up to be a really simple task, but they're kind of front, back, limbed, symmetric robots, the type of things that you saw in the earlier video are especially good for a very simple locomotion task. So it turns out that that this sort of bi-level optimization and even kind of our clever multi-objective version of this kind of nested bi-level optimization problem turns out to work really well. There's hidden complexity here that kind of puts it beyond a simple bi-level optimization problem, because if you switch this around and instead try and fine-tune the body for each new brain rather than vice versa, as we did before, there's no advantage to doing it this way. So there's something kind of privileged about the body, and I think that the way that it interacts with the environment in these brain-body environment systems. And I'm curious to see if we can find something similar about neural network architectures and how they kind of play a privileged role compared to optimizing the weights in our deep learning systems. So this is a lesson I learned the hard way. And let me just point out maybe one analogy of something that I think is a similar lesson in neural architecture search now. And I'll note that neural architecture search is a very diverse set of methods and interests in itself. And I'll focus here largely on supernet approaches, given that they're one of the popular and growing approaches now, and can feel very machine learning-y, differentiable all the way through. So with differentiable neural architecture search, or in this case, this particular figure comes from the original DARTS paper, and when trying to find the architecture and set of edges that connect a given set of nodes, the way that they do this is that they draw every possible connection that might exist, and actually kind of multiple versions of each connection for different nonlinear activation functions as well. And then train the weights of this supernet, and then also train the weighting of the architecture's weights on top of it. So which of these weights that we're training all together should be more important or not, and then use that subset of weights as the final architecture that we find. So this is a beautifully efficient and an ingenious idea by itself, but has kind of one major assumption, which is that while we're effectively looking at the composition of many different unique single architectures in this supergraph, the idea of weight sharing within these supernets implies that the weight of a network or the weight of an edge will be the same kind of regardless of which neural network it's embodied within, and that two different architectures that share the same weight or that share the same edge should have the same weight on that edge regardless of the other edges or other weights, which seems to be kind of the antithesis of what I've said before, of the kind of special co-optimization between structure and control, or in this case, topology and weights. Empirically looking at this, we've found that assumption maybe seems to be a bad one, or at least doesn't hold necessarily. And in this case, the algorithms that we found worked best in a survey were ones where the benefit of those algorithms, which is to say how far above this dotted random baseline they are, wasn't the case that high-performing supernet training algorithms were good at training weights that predicted well the performance of all architectures, but actually specialized to a very small subset of potential architectures, and in this case, the ones that turned out to be the good ones within the search space. So the idea that even a weight sharing network that's trained to try and be good across all potential topologies and architectures can't do that, I think is really telling. And there's some people who've identified this sort of problem before, and even fewer works that have tried to come up with simple ideas to encourage less generalization and more specialization in weights, but I think is a direction that would greatly benefit the field as a whole. So that was instance of training the shared weight model. Here, once we have a shared weight model optimized, if we then go and ask how you find the single neural network architecture that falls out of that, for the most part, people do what I said and just take the highest architecture weights from the resulting network. But it turns out that a large proportion of the time, almost half the time in the algorithms that we surveyed, just doing that wasn't the best approach. And there are kind of various different methods for selecting an architecture from a supernet that we found in the literature or proposed in this paper. And about half the time they do better than the version that was published in the original paper, especially for the original DARTS algorithm, which is notoriously bad at selecting architectures from its shared weight model. And so I think this is another kind of version of selection of architectures and shared weights being dependent on one another. To move on to the third point I want to rant about here, brain-body adaptation should occur at multiple timescales. So we saw this as a lesson of how we might be able to get around this idea of coupled systems before, looking at incorporating not just this evolutionary search but also fine-tuning. And I think that this is an idea we can push even further. So in bio-inspired robotics and evolutionary biology more generally, there are these ideas of very different timescales in which adaptation might happen, and behaviors that emerge at the interface of these different timescales. So kind of long-term evolutionary dynamics within lifetime learning and development, and also kind of behavior and action here and now. Again, starting with the simplest, most naive version of what this might look like, we coded up an evolutionary algorithm that specified not just a single robot morphology, but kind of two of them. One to start the robot's lifetime, one to end the robot's lifetime, and just very simply linearly interpolated between the two. So this is the lifetime change that we're now introducing from the systems above. And so we essentially kind of have the slow growth of the plant-like robot, but also the fast actuation of the others that we saw before. Now, much like we noticed in the last section, controllers have a hard time working on multiple different body plans. And it turns out that constantly changing your body while you're trying to run around is a very challenging thing. And our system where we evolve developmental patterns and plasticity does only about half as well as the version where we just evolve static body plans, at least at first. And then, comeback story of the year, the Evo-Devo approach finds some crazy behavior that's an order of magnitude faster at running around than the evolutionary approach. So we were really intrigued by this and tried to figure out kind of what it was about plasticity that was allowing such fast behavior. And it wasn't kind of any interaction within the behavior itself about plasticity and quick actuation, because the robots that had the highest performance, highest fitness within their lifetimes were ones that actually had very little plasticity, very small developmental changes during their lifetime. So it was something about kind of the broader landscape in evolutionary history that allows plasticity to interact with or guide evolution. And we see that looking at what end up being some of the best performing robots, that there's this trend of things kind of starting very plastic and then decreasing their plasticity over time, trying to lock in, canalize these high performing behaviors. But there's also something else interesting we found in this that I haven't heard talked about before in this literature. Which is that we actually saw spikes in developmental plasticity early on. And it's not that things are starting out extremely plastic, but there's some incentive or at least some random luck in evolutionary history that makes things more plastic over time, which is very counterintuitive to the prior plot showing that more plastic things perform worse. Yet there's some gradient here. There's some kind of minute advantage that evolution can latch onto, and the cause for that we tied to the Baldwin effect. So this is the idea that learning can guide evolution, and we've seen it demonstrated nicely in some machine learning papers, where we have some very hard to find exact behavior, some needle in a haystack that's extremely high performing when you can find it, but really hard to find. But if you have some sort of plasticity, some sort of hedging your bets by changing your body plan or the structure of your solution over time, there's some chance that you could start out close to it and find that needle in the haystack behavior. And by being more plastic, you're allowing yourself to have some chance of discovering this intelligent behavior. The case that we have again here is slightly more complicated because we're in an embodied setting. And so inspecting some of these behaviors, we start with our naive random behaviors. We evolve some nice walking, and depending on your frame rate on the Zoom call here, you might be able to see that at the very end of the lifetime, this robot dives forward like a runner stretching across the finish line, and learns to dive slightly better over time until that dive becomes a somersault, and that somersault becomes rolling, and suddenly we have a wheeled robot that's rolling across the screen instead of trying to walk across it. Now this would only be possible kind of in this evolution of development sort of way, because if you had a robot that tried to do this diving behavior at the beginning of its lifetime, diving towards the finish line, coming right out of the starting blocks, you'll just flop on your face and flail around, looking like an idiot in your race. But by doing it at the very end of the lifetime, the robot is able to take advantage of this local optima of diving and explore behaviors around that lead to rolling with actually very little consequence on the final fitness, because it doesn't matter if you're lying face down on the ground kind of once the trial ends. And so kind of especially related to the case of embodiment here, where you have consequences of past actions determining future ones, starting from the very end point and canalizing this behavior backwards, making rolling happen earlier and earlier is advantageous. And this is true, I think, of developmental systems, but also of learning systems more generally in ML, where the changes that you make early on in some lifetime learning process, the weight updates that you make will affect the gradients that you get later on in learning within some lifetime. And we find more systematically that this is true too, looking at the time before rolling for these creatures, that at the very end we have very little pressure, what we might call selection pressure in the evolutionary sense, and are able to do a lot of exploration here and find these good behaviors like diving and rolling before canalizing them and exploiting them to use them within the robot's whole lifetime as we progress on in evolutionary time over the x-axis here. So let me end by suggesting a way in which we might think about these multiple timescale approaches in neural architectures as one example of how we can take the ideas from embodied intelligence into machine learning. So there's a whole bunch of ways in which this might look. This is one that we're particularly fond of, but there's many others that we're working on too. So here we have not actually a typical neural architecture search setup where we're optimizing some network topology, but some masking behavior, more like pruning, and actually kind of most like attention, where we're doing some classification in our orange network at the bottom here. But instead of just feeding our input data into that classifier network, we're also feeding it into a second regulatory network in purple that decides for that piece of data which of the edges within our orange network should be active or not. So this is like a dynamic network architecture, so to say. We give this network a very challenging problem. Rather than feeding it all of the data at once in some nice IID shuffled fashion, we're going to do continual learning here, where we show lots of examples of one type of data and then lots of examples of another, never to return to some of the earlier classes again, but asking the model to be able to still perform well on them at the end of these long sequences. So this online continual learning task, we test by, after training, showing lots of examples of different classes that it's never seen in the same sort of sequential way. We're going to be particularly mean here and actually ask it to classify images of sequences, continual learning problems on ImageNet, but rather than meta training it on examples of ImageNet before, give it something much more sparse and totally different handwritten digits in the Omniglot dataset. So not only does it have to do continual learning for both, but this really dramatic domain transfer between meta training and then kind of testing and deployment as well. So to make this work, it took a lot of hyperparameter tuning. I'm surprised it even did work at all, to be honest with you. But one of the things that we found, again, kind of relates to the architecture search pruning philosophy here, which is that the regulatory network told an extremely small subset of our classification network to be turned on early on in learning. Virtually none of the network is active. Over meta-learning time, training on Omniglot here, more and more of the network is turned on, is allowed to participate until almost 20% of it is fully on for any given input image. And then the trend reverses, and we see some sort of pruning canalization behavior as fewer and fewer parts of the network participate in classification over time. I have no idea how and why this came about, but I was really excited to kind of draw the analogy between this and things like growth and pruning in biological neural networks that make me want to explore this idea much more. For a control, we started with networks that instead of being almost completely off, were half turned on, and it turns out that they show none of the same dynamics, with just kind of small fluctuations in participation over time, ending with about 60% of the network turned on at the end of things. So dynamics here were very different between the version that starts totally off and has to grow versus the one that we were kind of hoping would prune or sculpt away parts of the network. Had it started at that peak point partway through meta learning. When we switch to meta testing and give it a sequence of 100 ImageNet classes sequentially, kind of like the Evo case, interestingly, the growing network starts out not quite so good for shorter tasks or for shorter sequences, but for long sequences, drastically outperforms the other version of this same network, as well as some prior meta learning approaches. It gets even more crazy when we make the problem harder yet and give this network even less Omniglot data to train on. On the right here, it's just 3% of the meta training data. And this sparse initialized growing network seems barely affected, while the others catastrophically fail. Still trying to figure out exactly what's under the hood here, but I'm very interested and curious and wondering kind of what this tells us about developmental and meta learned topologies, and how what you learn early on affects later learning in the ways that we looked at with the evolutionary robotics case as well. There are all sorts of interesting phenomena we found in these networks, trying to explore them and figure out what the hell's going on. Here's one that I like, where the amount of the network that's turned on, exponentially bigger subsets are shown, are active exponentially less frequently in this really nice power law relationship, which may mean something, or may just be that power laws are present everywhere in natural and complex systems. That's a wrap on kind of my first pass at what an embodied intelligence perspective for neural architecture search might look like. That these topologies by themselves are powerful, that training them with their controllers is harder than we might think, but that multi-time scale algorithms might be a helpful tool as we think about approaching these sort of systems. Huge thanks to an amazing set of collaborators that have helped me throughout this journey, and thanks to you guys for your attention. I'd be happy to take any questions, or feel free to reach out to me by email afterwards as well.
Thank you, Nick, for the fantastic talk. Let's thank our speaker. Any questions? Okay, I can start with one. Fascinating talk, Nick, for reals. This is really exciting. So I can see that the connection between meta learning, where like you update, for example, your initialization as that initial architecture that you have, or the initial weight that you have, is really nicely fits through in the story of evolution, right? Like, but then I guess one thing that has bothered me in meta learning for a long time is that we usually don't talk about the diversity of tasks during meta learning, right? Like, so the meta learning, we say like we would like to find a network that can be rapidly adapted to all the tasks, but we can have bimodal distribution of tasks. So we may have tasks that are very far away from each other, but then they're similar here and they are similar there. So maybe there is no one network that can solve this task. So what will happen in those scenarios, right? Where like not a single, like, can we figure out two different networks in this case, or what we're going to end up finding is essentially like the average, which is not the good solution?
Yeah, that's a great question. So if meta learning worked as well as we wished it did, it would have no problem going and finding kind of very diverse tasks just through its inner loop within lifetime updates. Unfortunately, that's not the case, and like you say, we mostly find kind of the average of the behaviors and are able to do small amounts of fine tuning in between. It's possible. So there are certainly many meta learning approaches that we might want to take to kind of enable a wider diversity, mixture of expert sort of things, where you like have lots of behaviors that you might be able to fall back on. But from the perspective of this talk, maybe thinking about the evolutionary approaches to it, I can imagine cases where you don't necessarily always kind of start with the same initialization every time. That I'm trying to remember the exact species, but there's like a caterpillar where it develops into one phenotype if it's born in the spring, and one phenotype when it's born in the fall. And both of those kind of are subject to local growth and lifetime learning within them, but they're starting from very different points from the onset. And it's possible we could think of meta learning approaches that have an ensemble of these different starting points. But I think that's just kind of kicking the can down the road, and then it's kind of how many of these different meta initializations could we think of, but maybe it's also the case that we can take some inspiration from evolutionary theory, and think about kind of the fact that it's not always the case that we need to go out and solve a bunch of unique tasks kind of totally unrelated to each other, that we're, we kind of think of the selection of meta tasks as some IID process itself, where you could be randomly handed any other task. But, there's some curriculum, there's some shaping, there's some patterning, and even the structure of continual learning problems, that an RL agent isn't going to magically be transported into some other world and see something totally different, immediately after solving some task. And it might be the case that being adaptable to local changes within some developmental or inner loop learning process could help guide some meta learning process along kind of slower, more realistic changes across your task architecture within some schedule of learning too. I had one more point too, but I'm blanking. It'll come back to me in a second, but happy to go on to the next question. Unless you had another follow-up, Sylvia.
I have another one actually, right? So going to the continual learning experiment, I just want to understand a little bit more of the details, right? So the omniglot was used for training, but those grow, the results on the accuracy of the network that grew and then like pruned. So that one was pretty impressive. That was tested on ImageNet, right?
Yes, that was tested on ImageNet, and I should mention, I may have said this very quickly or even forgotten to, but this is the recall of training instances on ImageNet. The generalization validation sets do much worse than this. They show similar trends, but just overall performance is much lower.
Got it. Yeah, that's still pretty cool. Yeah. Right. Any other questions?
Well, I guess I can come up with one. So I think it was in the point 2 that you had, you showed a multi-objective approach. Mm-hmm. And I was wondering if you've looked at explicitly other types of structural or even behavioral diversity for these types of situations.
Yeah, so certainly there's many types of structural or behavioral diversity that we could think about, and kind of some of the details that got swept under the rug here is that we actually make very strong and very naive assumptions about structural and behavioral diversity that when I talked about how much time you have to fine tune to your new body plan. Well, it doesn't actually work if you consider a new body plan to be kind of any of those voxels or Jello cubes that change, but has to be kind of a gross change, a large scale one that in our case, I think we set the threshold of, you change 20% of the voxels in the robot. But obviously that's a very silly thing to do. And there's large changes that affect behavior very little and small changes that affect behavior very much. And the coupling is about kind of the structured behavior interactions. So there's definitely more nuanced ways that we can do that. It's also the case that we kind of draw the distinction between brain and body at some very precise black and white line, where kind of what's your brain and what's your body, I think is very unclear in biological systems, thinking about kind of centralized versus decentralized computation and even the nervous system, but is even more gray in these soft robots where for convenience, we actually use distributed controllers. So kind of each of these voxels has its own neural network and also its own material properties, and just decided to call some of the properties of the voxel materials and some of the properties of how it changed its shape over time control. But even more broadly to your point, this idea of kind of protecting innovations in the structure is an example of maintaining diversity within the population that we're evolving here. And there are many other ways of doing that, which oftentimes relate closer to behavior than to structure. Even the kind of early algorithms that I talked about in the space, kind of the neat approaches and many others have bio-inspired, niching or islands of different behavioral strategies that are allowed to develop on their own, kind of without selection from each other, which is exactly what we're imposing here with our multi-objective approach. So yeah, there's lots of related ideas around, and many of them have to do more with complex behaviors or descriptors of phenotypes than we have here.
Okay. Yeah, it seems like that's a challenging task to define these types of behavioral aspects.
Yeah, and actually one of the kind of intersections of evolutionary robotics and deep learning that I'm most excited about is that kind of thinking of good representations of behaviors or even kind of encodings for genomes is something that it seems like a neural network would be especially good at. And it's one of the things that we do very ad hoc and manually historically in evolutionary computation.
Okay. I guess a follow-up question would be if, I guess, thinking of like modular based approaches, I'm not so familiar. Have they fared better or worse generally?
Yeah, you're talking about kind of modular neural networks.
Yeah, and also with the structure. So kind of in both areas, I guess, just thinking of as compared to evolving the entire structure, but thinking of this in terms of different modules. Yeah,
absolutely. It's the case that that there are large structural changes that we want to add kind of potentially as modules like limbs. And that's kind of often how the design of robots was done before this work, was kind of having a number of prototypical things that you could stick together, rods and joints and whatnot. It's certainly the case that having clever modules to put together would be very much helpful. And the algorithm itself, which I didn't have time to go into at all, but is designed to try and make kind of large changes that kind of feel like adding a module where we're making something that's consistent at a high level, but changes lots of pixels at one time, because just switching out one at a time is kind of much too local to actually search over this space very well. So certainly that's something we wish we could do. It's a really hard kind of building block problem of even knowing what components you should be putting together to begin with, and how to assemble them. So this approach we've chosen, I don't think because it's best or most efficient, but maybe is most flexible. But I think that that idea also applies to the neural network controllers that we use also, where especially when you're talking about evolutionary approaches where we have to be making changes that are kind of viable every point and don't have gradient information. That modules are a great way at making what we call neutral mutations, where there's kind of not much happening to a large portion of the network, but kind of building up the ability to make subsequent mutations down the road. And so we've found that modular neural networks, maybe unsurprisingly, turn out to be much more robust and evolvable. And there's this really nice relationship actually between evolvability and robustness, that things like having modules of behaviors you can turn on and off turn out to be really helpful. And I would imagine that if we could find intelligent ways to make modules in the structure, that would be true as well. There's kind of really simple ways to make them in neural architectures that, just having like a L1 regularization, just having a penalty on connections turns out to evolve pretty modular networks, where I haven't seen kind of quite so easy a way to get it in structural motifs.
Okay. Yeah, it would make sense to kind of like come out of these local optimas that are found in the structure early on, and then just large fine tuning over the evolution. But okay, thanks.
So Nick, I have one more question. So for a lot of us who are not in the evolutionary computation, right, like we are more like on the gradient side of things, right, like using gradient-based methods. So can you give us an intuition about like the computational time needed for these evolutionary optimization, right? Like in our undergrad courses, we have all heard that evolution can take a lot of time and all that. So, but like, what are the most advances, like recent advances in the topic, and have they become faster, right? Like, how long does it take to train a model for a like, yes, let's say a standard neural network, like a ResNet something, ResNet 20, something like that?
Yeah, that's a great question. I would never advise someone to train a ResNet for ImageNet on with an evolutionary algorithm versus SGD. And actually, that much of my current work is trained with SGD, the things like the meta learning work that we've talked about here, just because it is so much more efficient. I think that the advantages for evolutionary computation and what got me so interested in it is kind of the intuitive nature that it can give to problems, that it's kind of very easy to kind of interact with and visualize the search process happening. And so actually kind of this example of building an intuition in some evolutionary sense, and then when thinking about how to make best use of it, think about how to translate those lessons into some gradient-based problem, I think for me is one of the best ways in which we could use this system. It's also very true that there are problems that are just really hard to get gradients on. That there's differentiable physics simulators now where it's we're getting slightly better at being able to design the structure of a robot, but it's still kind of way more difficult and convoluted to do so in a gradient-based way than it is when you could just look at an evolutionary output. And it's also the case that these two things don't have to be one or the other. That it's the case that you should always use SGD for training an image classifier, but there could be other things about your setup, kind of especially when we start to think about timescales, where it's really hard to design them, or there could be some advantage of doing it in an evolutionary sense. So we're thinking about some RL agent that we might want to be using, PPO or your favorite algorithm to actually be designing the behavior. But if you think about intrinsic goals or kind of the structure of the problem or things like that are kind of much more open-ended and require a lot more kind of branching and diverse options to think about, that maybe that's a better fit for an evolutionary approach. And kind of that mixed methods of the fact that we use reinforcement learning for ourselves, but yet kind of have evolved the structure to seek dopamine and hand it out to ourselves when we do things that are evolutionarily advantageous. I think is kind of a nice analogy to maybe how open-ended things could scale, is that it doesn't make sense to find behaviors in a divergent way, but it certainly makes sense to set goals in a divergent way. And evolution is a really nice divergent search. The only times when I would say actually use it for finding some good behavior are where your problem is just so messy that your gradients are awful and will lie to you all the time, which actually tends to be the case in some RL problems. And you saw kind of OpenAI's work of evolutionary strategies being as good or better than gradient descent in some of those cases.
Thank you. That's a fantastic answer. Thank you so much. Yep. Any other questions? Okay. I guess if not, thank you again, Nick. We went 15 minutes over. Yeah, we really appreciate your time. This was a great talk. Yeah.
Yeah, I appreciate it. Thanks for having me, and I can't wait till we can do this in person again.
Absolutely. Absolutely. Great. Thank you. Thank you, everyone.
Thanks.